Alright, so in this video we're going to talk about current and resistance. A couple terms that you've most likely heard, but perhaps not in the same context that we're about going to talk about here with electricity and stuff. So I've got a couple analogies to try to help explain this. Okay, the first one is called the water tower analogy, and if you look at a water tower, why do they keep the water up in this big tower? Well, the idea is if you keep the water up here, by the time it falls, okay, it produces some sort of pressure. Okay, so this is why I told you in the basic batteries video that you can sometimes think of potential difference or voltage as a pressure. If I hold the water up here, okay, it creates a lot of pressure into a smaller pipe down here. I mean, why does the water come flying out of your faucet? Well, because there's a lot of potential up here and it forces it down pretty hard. Okay, so if this water up at this height is representing the potential, then the pipes that the water flows through, okay, the actual width of the pipe is providing some resistance to the flow of the water. Okay, so that pipe itself is considered a resistance, and then how fast the water comes out of the pipe is the current. Okay. Now, in terms of electricity, the voltage is the potential difference in the battery itself. The resistance is going to be the objects that the electrons have to flow through, and then the current is the actual rate of flow of those electrons. Now, we can have another analogy talking about people exiting a room. So let's say everybody was down in the gym and there was a fire alarm. Okay, well, all the people rushing to get out of the room is the potential difference. Okay, how many doors are open would represent the resistance, because if there's only one door open, it's going to be hard to get everybody through one door. The more doors that open up, the less resistance there is. Okay, and then the rate at which people flow out of the door would be the current. Okay, so the basic definition here of current is the flow of electrons. Okay. Now, we do have to talk about types of current. There's conventional current and electron current. Okay. Conventional current tends to be the one that most people use. And if you look here, conventional current is in the direction that a positive charge flows. Now, keep in mind that current is really caused by the movement of electrons, which are negative. However, current usually is described in the direction that positive charges would flow. Not a big deal, but in my drawing here, you'll notice I've got away from the positive terminal, okay, leading away. A positive charge would lead away from the positive terminal to the negative terminal. Therefore, conventional current flows from positive to negative, whereas electron current would go from negative to positive. Generally shown, this is the direction of the current, from positive to negative. So the basic definition of current is given right here. The symbol for current is I. If you look at this, I is the change in charge over the change in time. It's the rate of change, the time rate of change of the charge itself, how fast those charges are flowing. Okay, the flow of electrons. So units. You can have coulombs per second, which is better known as an ampere or an amp, or simply the letter A to represent amps. Okay. One little note here: more often you're going to see milliamps than full amps, at least in the majority of problems that we do. Not to say that you're not going to see full amps, but milliamps is relatively common. Okay. All right. So resistance. Okay, resistance is the restriction of the flow of electrons. And the basic definition, and resistance gets capital R, or basic equation for it, is the voltage divided by the current. So that's volts per amp, or better known as this symbol, which is called an ohm. Okay, and this is omega, and then this is an ohm. Okay. pretty simple formula. Resistance is provided by resistors, okay, which is a device that controls that particular current, controls how fast it flows. And you're going to see a couple different symbols in these circuit diagrams. Like up here in this circuit diagram, I've just got a battery with a light bulb in it. So this light bulb technically is a type of resistor, okay, but I could redraw this with just the little squiggly line in there if it was AP, or just the little box if it was IB. Okay, that's how it's going to show up. If you've ever looked at a resistor, they usually have these color stripes on them. That's because there actually is a resistor code to figure out the actual value of the resistor. I'm not going to require that you know that by any means, but in case it pops up in like a question or something like that, please look at page 499 in your G and Coley book as a reference. Okay, then the next thing I want to talk about is resistivity. What exactly dictates the resistance of an object? Okay, and there's a formula for it. This is symbol rho times the length divided by the area. Now, what exactly is this particular symbol? This symbol is given in ohms times meters. It's defined as the constant of proportionality, which is strictly dependent on the material itself. And you're going to need those values. So in your book, in your G and Coley book, they're on page 501 if you need to look them up. Okay, and then this area, if it's a wire, the area is a cross section of that particular wire. So you're looking at a circle of some sort. So the area of that would be pi r squared if you wanted the area of that circular cross section. Okay, now, if we were using, not a circular or a cylindrical type of resistor, if we were using a box resistor, then you would only need the basic form for area, which is base times height. Okay, so the actual shape of the resistor does matter. Now, I'd like to point out that the resistivity, or the resistance of an object, is proportional to the length. Okay, so the longer the wire, the higher the resistance. But it's inversely proportional to the area, meaning the bigger the area, the smaller the resistance. Okay, so just so you're aware of those things. Now, one other thing I want to make note of, and we'll touch on this maybe a little more later, that resistance increases with temperature. And I always feel like that seems contradictory, because you're more used to thinking of, okay, when things are hotter, they flow easier, okay? But these are electrons that we're talking about flowing, and the more atoms that are moving around, if they're moving around more, there's technically more atoms for the electrons to run into. Therefore, if the temperature increases, resistance also increases. Okay? All right. And then the very last thing that I have for you in this particular section is some little hints and vocab, so that when we say them, or when you hear them in a problem, they make sense. Okay, and they might still not make sense even after this video, but we'll hit on these, and I just want you to keep these in your mind. Okay, so the first one on here says, a potential difference from point A to point B is often referred to as a potential drop. Okay, so if you've got 2 points, okay, the difference in those potentials from either points is referred to as a potential drop from A to B. Okay. Number 2 on here says voltage is applied across a wire or device. Okay. It's not found in any specific area. It's applied across the device. Okay. And then number 3, current passes through a wire or a device. Current goes right through it. And then the last one also says that current doesn't get used up. Whatever the current into a junction is going to be the current out of the junction. And these things are going to make more sense as we start doing circuit diagrams, but I just want you to be aware of this vocabulary so that when it does show up, you're not completely lost by it. Okay?